Time moves forward, relentless and unyielding, carrying the universe from its fiery birth to a distant, quiet end. Stars burn, galaxies spin, and planets turn. But this cosmic dance is not eternal. Everything decays, from the smallest atom to the grandest galaxy, far beyond our lifetimes. In a future spanning trillions of years, the universe will transform, its familiar rhythms fading into a cold, silent stillness, a reality where the laws of physics play out to their strangest conclusions. The universe we know is alive with light. At night, the sky glimmers with stars, each a furnace fusing hydrogen into helium, casting warmth across vast distances. These stars, scattered through billions of galaxies, are the heartbeat of the cosmos, their glow a blend of a universe in its prime. But this brilliance is temporary, a fleeting moment in a story that stretches far beyond human comprehension. Stars are not eternal, they are engines with finite fuel, destined to burn out, leaving behind a darker, quieter universe. Stars are born in clouds of gas, collapsing under gravity to ignite in nuclear fusion. A star like our Sun burns steadily for billions of years, its core a cauldron where hydrogen fuses into helium, releasing energy that lights the heavens. But fuel runs low. When hydrogen dwindles, the core contracts, heating to fuse helium into carbon and oxygen. The star swells into a red giant, its outer layers glowing crimson, before shedding them to form a planetary nebula, leaving a white dwarf, a dense, cooling core no larger than Earth. This fate, mapped in the 1930s by Subrahmanyan Chandrasekhar, applies to stars below a critical mass, now called the Chandrasekhar limit. Heavier stars meet a more dramatic end. When their cores exhaust fuel, they collapse under gravity, triggering a supernova explosion that outshines entire galaxies. The core may become a neutron star, a city-sized sphere of unimaginable density, or a black hole, a void where gravity traps even light. Chandrasekhar's calculations showed that stars above the limit follow this path, their remnants enduring long after the explosion fades. These processes fusion, collapse. Explosion are the universe's machinery, but they rely on finite resources, and the cosmos is running out of raw materials. The universe was once a nursery of stars, with vast gas clouds birthing new suns in a frenzy of creation. But those clouds are depleting. Each star formed consumes gas, and supernovas scatter some into space, but much is locked away in white dwarfs, neutron stars, and black holes. Over billions of years, the star formation rate slows, a trend already observable today. In 10 trillion years, the galaxies will birth fewer stars, their fuel reserves nearly spent. By 100 trillion years, the process will nearly halt, leaving a universe where new light is a rarity. This decline is not sudden, but gradual, a fading glow across cosmic time. Stars like our Sun, with lifespans of 10 billion years, will be long gone. Even red dwarfs, the smallest and slowest burning stars, which can shine for trillions of years, will eventually exhaust their hydrogen, their fusion will falter, and they'll cool into white dwarfs, joining the silent remnants of their brighter kin. The last red dwarf, perhaps the final spark of warmth, will flicker out in a future so distant it defies imagination, marking the end of the stellar era. What remains is a universe of leftovers. White dwarfs, now cold and dark, drift through the void, their surfaces no longer glowing. Neutron stars, dense and silent, spin slowly, their magnetic fields faded. Black holes, the densest relics, lurk in the darkness, swallowing stray matter. Rogue planets, ejected from their systems, wander frozen, their surfaces locked in eternal ice. These objects, scattered across a universe stretched thin by expansion, are the cosmic fossils of a once vibrant epoch, a testament to the impermanence of light and heat. This phase, known as the degenerate era, is a stark departure from the universe we know. There are no galaxies aglow with starlight, no nebulae birthing new suns. Space is vast, its distances growing as the universe expands, driven by dark energy that pushes everything apart. The galaxies, once tight spirals and clusters, have merged or drifted, their stars extinguished. What's left is a cold, quiet expanse, where objects are so far apart they rarely interact, a universe where motion slows and energy fades. The degenerate era underscores the universe's entropy, the tendency for order to dissolve into disorder. Stars once drove energy from hot cores to cooler surfaces, powering fusion and light. But in this era, there's no heat to flow, no gradient to fuel work. White dwarfs and neutron stars, though dense, are inert, their energy spent. The universe is not dead in a dramatic sense, but still, like a clock wound down so far, it cannot tick. Matter exists: black dwarfs, neutron stars, rogue planets, but it's meaningless, isolated, unable to form new systems or spark new life. This stillness is a natural outcome of physics, not a break from it. Thermodynamics dictates that energy disperses, that systems decay. The universe, following these rules, has run its course, its vibrant youth replaced by a quiet middle age. Yet this is not the end. The degenerate era, stretching across unimaginable timescales, is a prelude to stranger transformations. Black holes, the brilliant giants of this epoch, will play a role. Their slow decay a sign that even the densest objects are not eternal. The human perspective on this future is humbling. We live in a fleeting moment, a time when stars still shine, when galaxies still dance. Our lives, measured in decades, are a blink against the trillions of years that lie ahead. Yet we imagine this future, tracing the path of physics to its limits, asking what becomes of the cosmos when all we know is gone. This is a deeply human act, a search for meaning in a universe that will outlast us, a reflection on our place in a story that began with light and will end in silence. The melancholic beauty of this narrative lies in its inevitability. The stars, so bright today, are destined to fade, their light a temporary gift. The galaxies, vast and swirling, will dissolve into the dark, their stories lost to time. Yet there is wonder in this decay, in the way the universe follows its laws with unwavering precision, transforming from a blaze of creation to a quiet drift of remnants. The degenerate era, with its cold relics, is a testament to this transformation, a stage where the cosmos rests before its next act. This journey through the universe's decline is a reminder of our fleeting existence. The stars that guide our nights, the galaxies that fill our telescopes, are part of a brief chapter, a moment when the universe is alive with possibility. As we look to the future, we see not just the end of light, but the persistence of physics, the rules that carry the cosmos forward even as it grows cold. The story of the universe's end is not yet complete. Its next phase waiting in the shadows, ready to unfold in ways that challenge our understanding of reality itself. The universe, once aglow with stars, has faded into a cold, dark expanse, its galaxies dimmed and its starlight extinguished. In this vast silence, black holes emerge as the silent rulers, their immense gravity shaping a cosmos stripped of warmth and motion. Over timescales stretching beyond imagination, these enigmatic relics decay through a subtle process, revealing a universe where even the mightiest structures surrender to the relentless march of time. The degenerate era, where white dwarfs and neutron stars drifted in isolation, has given way to a new chapter, the black hole era. Stars are gone, their fusion silenced, leaving behind a universe of remnants. Galaxies, once vibrant spirals, are now dark, their light lost to the cooling of red dwarfs and the collapse of massive suns. In this emptiness, black holes stand as the last bastions of structure, formed from the deaths of stars, galactic collisions, or the merging of smaller voids. They are not mere objects but gravitational giants, warping space-time so fiercely that nothing, not even light, can escape their grasp. Black holes are the universe's long-term survivors, enduring where stars and planets have faded. A stellar mass black hole, born from a supernova, may have the mass of 10 suns compressed into a point smaller than an atom. Supermassive black holes, lurking at galactic centers, hold the mass of billions of suns, their influence stretching across light years. In the black hole era, these objects dominate, scattered across a universe expanded so vastly by dark energy that galaxies are mere memories, their remnants spread too far to interact. Gravity drives this epoch's slow ballet. Black holes drift, their paths shaped by the faint pull of distant masses. Some collide, merging to form larger voids, their event horizons rippling as they coalesce. Others accrete stray matter rogue planets, cold dwarfs, or cosmic dust drawn too close by gravity's unyielding embrace. These interactions are rare, as space has stretched to isolate most objects. But when they occur, they are moments of cosmic drama, brief sparks in an otherwise silent void. Over trillions of years, even these collisions dwindle, leaving black holes as solitary sentinels in a universe grown impossibly vast. This era is not eternal, for black holes, despite their might, are not immune to decay. In the 1970s, Stephen Hawking revealed a startling truth. Black holes evaporate through a process now called Hawking radiation. The vacuum of space, far from empty, is alive with quantum fluctuations, where virtual particle pairs matter and antimatter briefly appear and annihilate near a black hole's event horizon, the boundary beyond which nothing escapes. These pairs can be split. One particle falls into the void, while the other escapes, carrying a sliver of the black hole's energy. This escaping particle, a photon or other lightweight entity, slowly drains the black hole's mass. Hawking radiation is vanishingly slow. For a stellar mass black hole, the process takes 10 to the 67th years, a number so vast it dwarfs the universe's current age of 13 billion years. Supermassive black holes, with their greater mass, require even longer, up to 10 to the 100th years. A timescale that makes the degenerate era seem fleeting. Each radiated particle is a minuscule loss, but over these immense spans, the losses accumulate, shrinking the black hole until it vanishes in a final burst of radiation, a quiet puff rather than a cataclysmic explosion. This evaporation is a triumph of quantum mechanics, showing that even black holes, the universe's most unyielding structures, are subject to the laws of physics. The process is imperceptible on human timescales, but in the black hole era, time is no constraint. The universe, patient and indifferent, waits as black holes fade, their mass converted into a thin spread of photons and other particles. As the last black hole evaporates, the cosmos loses its final anchors of gravity, leaving a near-perfect vacuum, a stage where the actors have departed and only the faintest traces remain. The black hole era is a study in contrasts. Black holes are both eternal and ephemeral, dominating the universe for eons, yet doomed to dissolve. They are invisible, their presence known only by their gravitational pull, yet they shape the cosmos' structure, gathering matter and merging in silent dances. Their decay, through Hawking radiation, is a microcosmic process, quantum fluctuations at the event horizon, yet it plays out on the grandest scales. transforming the universe over unimaginable timescales. This interplay of the small and the vast is a hallmark of the cosmos's evolution, a reminder that even the mightiest entities are bound by the same rules that govern the smallest particles. The human perspective on this era is one of awe and humility. We live in a time of light, where stars illuminate the night and galaxies tell stories of creation. The black hole era, by contrast, is a future where light is a memory, where the universe is a graveyard of gravitational ghosts. Our existence, a mere flicker in cosmic time, seems insignificant against the backdrop of 10 to the 100th years. Yet we imagine this future, piecing together its story through equations and observations. This act of imagination, of reaching across eons to understand the cosmos's fate, is a deeply human endeavor, a search for meaning in a universe that will outlast us all. The melancholic beauty of the black hole era lies in its quiet persistence. The universe, stripped of its stars, continues its slow transformation, driven by gravity and quantum mechanics. Black holes, once symbols of destruction, become relics of endurance, their evaporation a gentle farewell rather than a violent end. This era, spanning timescales beyond comprehension, is a testament to the universe's patience, its ability to follow its laws through the darkest, most silent phases of its existence. The black hole era also raises profound questions about information and loss. As black holes evaporate, what happens to the information they held? The details of the matter they consumed. Hawking initially argued this information was lost, but later theories suggest it may be preserved in the radiation, encoded in ways we cannot yet fully grasp. This debate, central to modern physics, hints at deeper truths about the universe's structure, truths that may persist even as black holes fade. The question of information's fate is a thread that will weave into the cosmos's later stages as the universe grows emptier still. The end of the black hole era marks a turning point. With the last black hole gone, the universe is a near-empty void, its only contents a scattering of subatomic particles and radiation, stretched thin by relentless expansion. This is not the final act, but a transition, a stage where the absence of structure allows new physics to emerge. The particles that remain, the relics of stars and black holes, face their own decay, setting the scene for a cosmos where even the building blocks of matter may not endure. This journey through the universe's decline is a reflection on permanence and change. The black holes, so dominant in this era, are not eternal. Their decay, a reminder that nothing escapes the laws of physics. The cosmos, once a place of creation, is now a realm of dissolution, yet its story continues, driven by the quiet persistence of quantum processes and the inexorable stretch of space. As we look to the future, we see a universe poised for stranger transformations, where the rules of reality may shift in ways that challenge our deepest understanding. The universe, stripped of stars and black holes, lingers as a vast, cold void, its only remnants a scattering of particles adrift in endless space. In this desolate expanse, even protons, the sturdy cores of atoms, may decay, unraveling the last traces of matter into a faint sea of radiation. This quiet dissolution, unfolding over unimaginable timescales, transforms the cosmos into a realm where solidity vanishes, leaving only whispers of what once was, a testament to the impermanence of all things. The black hole era has ended, its final voids evaporating into photons through Hawking radiation, leaving a universe nearly empty. White dwarfs, neutron stars, and rogue planets persist, cold relics of a bygone age, but they are sparse, isolated by the relentless expansion driven by dark energy. These remnants, once part of vibrant galaxies, now drift in a cosmos stretched so thin that interactions are rare. The universe is a silent archive, its history etched in these frozen fossils, but even they are not eternal. A new process, proton decay, threatens to erase the last vestiges of matter, ushering in a post-decay radiation era. Protons are the backbone of atoms, residing in their nuclei alongside neutrons, surrounded by electrons. Their stability has long been assumed, a foundation for matter's endurance. Every rock, every planet, every neutron star depends on protons' permanence. Yet grand unified theories, developed by physicists like Howard Georgi and Sheldon Glashow in the 20th century, suggest protons may not last forever. These theories, which aim to unify the strong, weak, and electromagnetic forces, predict that protons decay into lighter particles, positrons, photons, or neutrinos over timescales so vast they dwarf the black hole era. The predicted lifetime of a proton is staggering, at least 10 to the 34th power years, a number that makes the universe's current age of 13 billion years seem instantaneous. This is not a process we can observe. No experiment has yet detected proton decay, and the odds are so low that a single proton's decay is a cosmic rarity. But in a universe with infinite time, rarity becomes certainty. Given enough protons and enough years, trillions of trillions, the decay accumulates, each proton crumbling silently, its energy released as fleeting radiation. In the post-black hole era, the universe's remnants are prime candidates for this decay. Black dwarfs, the cooled husks of white dwarfs, are dense with carbon and oxygen nuclei, each packed with protons. Neutron stars, though dominated by neutrons, contain proton-rich layers. Rogue planets, frozen worlds of rock and ice, are built from atoms with proton cores. Over 10 to the 35th years, these objects begin to disintegrate, not through violence, but through a slow, statistical unraveling. Protons decay, their nuclei breaking apart, leaving positrons and photons that scatter into the void. This decay is not a fiery end, but a quiet erosion. A black dwarf, once a solid sphere, loses its structure as protons vanish, its matter dissolving into a diffuse cloud of radiation. A neutron star's proton-rich surface crumbles, its stability fraying. By 10 to the 40th power years, most protons are gone, their decay complete. What remains is a universe without atoms, without solids, without the building blocks that once formed stars and planets. The cosmos is now a thin, ghostly expanse, filled with photons, neutrinos, and other lightweight particles, stretched ever thinner by expansion. This post-decay radiation era is a stark departure from the universe's earlier vibrancy. There are no galaxies, no stars, no black holes, only a near-empty vacuum where particles drift, too distant to interact. The universe's energy, once concentrated in fusion and gravity, is now diffuse, a faint hum of radiation that carries no warmth, no potential for creation. This is entropy at its extreme, where the cosmos has no gradients left to fuel change. The particles exist, but they are meaningless, a silent testament to a reality where matter has lost its purpose. The physics of proton decay is a triumph of theoretical insight, rooted in the Standard Model and its extensions. Grand unified theories, proposed in the 1970s, suggest that at high energies of the early universe, the fundamental forces were one. As the cosmos cooled, these forces split, but protons retained a faint instability, a memory of that unity. The decay process, though speculative, follows from these principles, a prediction that no new forces are needed, just the slow, inevitable work of quantum mechanics over eons. If protons are stable, As some models allow, the universe might linger longer in its degenerate state, but the possibility of decay paints a bleaker, more transient picture. The human perspective on proton decay is one of profound disconnection. We live in a world of matter, where atoms form the ground beneath us, the air we breathe, the stars we see. The idea that these atoms could dissolve, not in a cataclysm, but in a slow, silent fade, challenges our sense of permanence. Our lives, measured in heartbeats, are infinitesimal against 10 to the years, a timescale that renders human existence a fleeting whisper. Yet we ponder this future, using mathematics to trace the cosmos's path, a testament to our need to understand even what lies beyond our grasp. The melancholic beauty of this era lies in its quiet dissolution. The universe, once a place of creation, is now a realm of decay, where even the sturdiest particles surrender to time. The post-decay radiation era, with its sparse, drifting particles, is a cosmos stripped bare, its vibrancy replaced by a stillness that feels eternal yet fragile. This is not an end, but a transition, a stage where the absence of matter sets the scene for stranger possibilities, where the universe's very fabric may shift in ways we cannot predict. The human connection to this narrative is both humbling and profound. We are made of protons, our bodies a temporary assembly of atoms destined to outlast us, yet not forever. The idea that these atoms could decay, leaving only radiation, mirrors our own impermanence, a reminder that all things, from stars to selves, are bound by the same laws. Yet, in imagining this future, we assert our place in the cosmos, our minds reaching across eons to grapple with a reality that will unfold long after we are gone. The post-decay radiation era also raises questions about information and existence. As protons decay, do they leave a trace of their history, or is their information lost? The debate over black hole information, sparked by Stephen Hawking, finds an echo here. As the universe's final particles fade into the void, these questions, rooted in quantum mechanics, hint at deeper truths about the cosmos's structure, truths that may persist even as matter dissolves. The radiation that remains, stretched thin by expansion, is a faint archive, carrying the universe's story into its next, stranger phase. This journey through the universe's decline is a reflection on change and loss. The protons that built our world, so stable in our time, may crumble, their decay a quiet end to matter's reign. The cosmos, now a sea of radiation, is poised for further transformations, where the rules of physics may bend in ways that defy our understanding. The story of the universe's end continues, its next act waiting in the silent expanse, ready to unfold in a reality where even emptiness holds secrets. The universe, reduced to a faint sea of radiation, stretches endlessly, its matter dissolved and its forces silenced. In this near-empty void, a subtle instability looms: vacuum decay, a quantum shift that could rewrite the laws of physics themselves. This silent transformation, lurking in the cosmos's deepest future, threatens to erase the last vestiges of our reality. A final act where even the fabric of existence may unravel, leaving a universe unrecognizable. The post-decay radiation era, where protons have crumbled into photons and neutrinos, marks a cosmos stripped of structure. No stars, no black holes, no atoms, remain only a sparse, cold expanse, its particles too distant to interact, spread thin by relentless expansion. This is a universe at maximum entropy, where energy gradients have vanished, and change seems impossible. Yet, even in this stillness, the vacuum, the underlying field that defines space, is not inert. It holds a hidden fragility, a potential to shift into a state that could alter reality's foundations, a process known as vacuum decay. The vacuum is not empty but a dynamic stage, shaped by fields like the Higgs field, which gives particles their mass. The Higgs field, discovered in 2012, sets the rules for our universe, allowing atoms to form, stars to burn, and life to exist. Its value, finely tuned, creates a stable reality, but stability may be an illusion. Theoretical physicists, including Gianfrancesco Giudice and John Ellis, calculated that our vacuum might be metastable, not at its lowest energy state. A deeper, more stable vacuum could exist, and if our universe's vacuum were to shift to this state, the consequences would be profound. Vacuum decay begins with a quantum fluctuation, a random blip in the fabric of space where the Higgs field's value changes. This fluctuation creates a bubble of true vacuum, a region governed by new physical laws. Unlike our vacuum, where particles have specific masses and forces interact predictably, this new state could render atoms impossible, disrupt gravity, or erase time itself. The bubble, once formed, expands at nearly the speed of light, converting the surrounding metastable vacuum into its own reality. There's no explosion, no heat, just a silent replacement, a rewriting of existence itself. This process is not a distant fantasy, but a consequence of quantum mechanics, where probabilities govern even the universe's fate. The likelihood of vacuum decay is vanishingly small, so low that it might not occur for 10 to the 100th power years, a timescale that dwarfs proton decay's 10 to the 34th power years. Yet, in an infinite universe, even the smallest odds become certainties. The vast emptiness of the post-decay era, with its endless space and time, offers countless opportunities for a fluctuation to spark a bubble, transforming the cosmos in an instant. The implications of vacuum decay are staggering. Inside the bubble, the laws of physics could be incompatible with matter, energy, or structure as we know them. Electrons might lose their charge, gravity might weaken, or space itself might collapse. The universe we know its constants, its forces, its very essence would vanish, replaced by a reality we cannot predict. It might be a flat nothingness, a void without form, or a new cosmos with alien rules, where stars and life are impossible. This is not destruction but irrelevance, a shift where our physics becomes a forgotten footnote. The human perspective on vacuum decay is both unsettling and awe-inspiring. We live in a universe where the Higgs field's delicate balance allows our existence, a fleeting moment of stability in a cosmic timeline that stretches beyond comprehension. The idea that this balance could shift, not through cataclysm but through a quiet quantum event, challenges our sense of permanence. Our lives, our world, our entire reality could be erased, not by force, but by probability, a reminder of our fragility in a cosmos governed by chance. The science of vacuum decay is rooted in the Standard Model and its extensions. The Higgs boson's mass, measured at the Large Hadron Collider, suggests our vacuum is near the edge of metastability, a precarious state where a lower energy vacuum is possible. Calculations by Giudice and Ellis show that our universe's constants, the Higgs boson's mass, the top quark's properties, place it uncomfortably close to instability. While we may be safe for eons, the possibility of decay is real, a prediction that requires no new physics, only the quantum rules that govern our reality today. The melancholic beauty of vacuum decay lies in its silent inevitability. The universe, already stripped of stars and matter, faces a final transformation, not through violence, but through a subtle shift in its essence. The post-decay radiation era, with its sparse particles, is a cosmos on the brink. Its vacuum, a fragile canvas waiting for a quantum brushstroke. This is a story of endings, where even the rules that define existence may fade, leaving a reality where nothing familiar remains. The human connection to this narrative is profound. We are products of a stable vacuum, our atoms and thoughts shaped by the Higgs field's delicate balance. The idea that this balance could collapse, erasing the physics that sustains us, mirrors our own mortality. A reminder that all things, from particles to people, are temporary. Yet in pondering vacuum decay, we assert our place in the cosmos, our minds reaching across unimaginable timescales to grapple with a future that defies comprehension. This act of imagination, of seeking meaning in the face of nothingness, is a deeply human endeavor. The implications of vacuum decay extend beyond our universe. If a bubble forms, it might not be the first. The cosmos could be part of a multiverse, where other bubbles have sparked new realities with different laws. This idea, explored by physicists like André Linde and Alexander Vilenkin, suggests our universe is one of many, each born from a quantum fluctuation in an inflating landscape. Vacuum decay, then, is not just an end, but a potential beginning, a branching point where new universes might emerge, each with its own story. The question of information persists in this era. As the vacuum shifts, what happens to the universe's history, the details of stars, planets, and lives? The debate over black hole information, where data may be preserved or lost, finds an echo here. If our vacuum decays, the information encoded in our reality, every particle's spin, every photon's path might be erased or transformed, a loss that raises profound questions about the nature of existence. These questions, rooted in quantum mechanics, will carry into the cosmos's final phase, where even emptiness holds possibilities. This journey through the universe's decline is a reflection on fragility and change. Vacuum decay, a quiet shift in the cosmos's foundation, threatens to erase the rules that define our reality, leaving a universe where the familiar is irrelevant. The cosmos, now a near-empty void, is poised for its strangest act, where quantum mechanics and probability take center stage, shaping a future where even nothingness may give rise to something new. The story of the universe's end continues, its final chapter waiting in the silent expanse, ready to unfold in ways that challenge our deepest understanding. The universe, a near-empty void of fading radiation, drifts in silent expanse, its reality teetering on the edge of quantum uncertainty. In this final epoch, random fluctuations spark fleeting structures, particles, minds, even new universes, while time itself loses meaning, dissolving into a timeless stillness. This journey, from starlight to nothingness, reflects humanity's quest to understand a cosmos that outlives us, a narrative of endings and possibilities, where the silent folds of space whisper eternal questions. The vacuum decay era, where the universe's physical laws could shift, has left a cosmos stripped bare, its protons decayed, its black holes evaporated, its stars and galaxies long gone. Only a faint scattering of photons and neutrinos remains, spread so thin by relentless expansion that interactions are impossible. This is a universe at its most desolate, a realm where entropy reigns supreme and change seems a distant memory. Yet, even in this emptiness, quantum mechanics persists, its probabilistic nature sparking rare, strange events that challenge our understanding of existence, time, and reality itself. Quantum fluctuations, the universe's last actors, are the heart of this epoch. In the vacuum, space is not truly empty, but a seething field of virtual particles, popping into and out of existence in fleeting pairs. Normally, these pairs annihilate instantly, leaving no trace. But in a universe this vast and quiet, their effects linger. Over time scales beyond comprehension, 10 to the 100th power years or more, these fluctuations can produce not just particles, but complex structures. A single atom, a molecule, or even a fully formed brain could emerge. A phenomenon known as a Boltzmann brain, named for Ludwig Boltzmann's 19th century work on statistical mechanics. Boltzmann brains are not science fiction, but a statistical inevitability in an infinite universe. Given enough time, quantum randomness can assemble anything, no matter how improbable. A brain, complete with memories of a life it never lived, might flicker into existence. Think for a moment, then dissolve back into the void. These are not living beings, but fleeting mirages, their thoughts as transient as the fluctuations that birthed them. The paradox is unsettling in this future. Such random minds might outnumber those that evolved naturally, raising questions about consciousness and reality. If most minds are Boltzmann brains, are our own thoughts mere statistical blips? This epoch is not just about brains, but about possibility. Quantum fluctuations could spawn not just particles, but entire regions of space with new physical laws. A fluctuation might trigger a quantum tunneling event, shifting a patch of vacuum to a different state, potentially birthing a new universe. This idea, explored by physicists like Andrei Linde and Alexander Vilenkin, suggests our cosmos is one bubble in an eternally inflating multiverse, where new universes form as others fade. These bubbles, stable or fleeting, could carry alien physics, their constants and forces unlike our own, each a fresh start in a cosmic forest of possibilities. The concept of time itself falters in this era. Time, as Sean Carroll and others have argued, is tied to entropy, the arrow from order to disorder, in a universe at maximum entropy, where no gradients drive change. Time's direction blurs. Without events to mark one moment from another, no stars forming, no particles colliding, time becomes a frozen frame, a paused video with no motion to distinguish past from future. Quantum fluctuations, like Boltzmann brains or new universes, are too rare and isolated to create a narrative, leaving a cosmos where time exists but lacks meaning, a silent ticking without a clock. Reflecting on this narrative, we see a universe transformed from a blaze of starlight to a quiet void, its story unfolding through inevitable decay. The stars faded, their fuel spent, leaving white dwarfs and neutron stars in a degenerate era. Black holes ruled, then evaporated, their mass lost to Hawking radiation. Protons decayed, dissolving matter into radiation. And vacuum decay threatened to rewrite physics itself. Now, quantum fluctuations spark fleeting structures, a final act where randomness reigns. This journey, spanning trillions of years, is a testament to physics' unyielding logic, each phase a consequence of the laws that govern our reality today. The human connection to this story is profound. We are fleeting beings, our lives a blink against the cosmos's timeline, yet we imagine its end, tracing its path through equations and theories. This act of imagining, of seeking meaning in a future we'll never see, is uniquely human, a reflection of our curiosity and resilience. We are made of atoms destined to decay, yet we ponder a universe that outlives us, finding wonder in its silence. The Boltzmann brain paradox, with its ghostly minds, mirrors our own fleeting consciousness, a reminder that even our thoughts are temporary, yet precious for their rarity. The melancholic beauty of this epoch lies in its stillness. The universe, once vibrant with galaxies, is now a canvas of nothingness, its only motion the rare flicker of quantum chance. These fluctuations, sparking brains or universes, are not beginnings but echoes, moments that fade without legacy. The cosmos, stripped of structure, is a silent witness to its own decline, its vastness a monument to what was lost. Yet there is hope in this emptiness, a possibility that new realities may emerge, each a fresh chapter in an eternal story. The scientific foundation of this era is rooted in quantum mechanics and cosmology. Boltzmann's statistical mechanics, developed in the 1800s, showed that order can arise from disorder. Given infinite time, Lindy and Villenkind's eternal inflation, proposed in the 20th century, suggests a multiverse where universes bubble endlessly. These ideas, grounded in observation and mathematics, predict a future where randomness governs, where the improbable becomes possible. The absence of time's arrow, as Carroll's work on entropy implies, completes this picture, a cosmos where change ceases, and existence becomes a statistical dream. The question of information persists as particles decay and vacuums shift. Is the universe's history every star's light, every planet's orbit preserved or lost? The black hole information paradox, where data may be encoded in radiation, finds an echo here. As the cosmos's final fluctuations carry no record, this loss, or potential preservation in quantum entanglements, raises profound questions about memory and meaning, questions that linger in a universe without observers. The Boltzmann brain, a mind without context, underscores this, its thoughts a fleeting illusion in a reality without history. Looking to the future, this epoch is both an end and a question. The universe may drift forever, its fluctuations too rare to matter, or a new bubble might spark a cosmos with new laws. The multiverse, if real, suggests our story is one of many, each universe a fleeting experiment in an inflating landscape. This possibility, though unprovable, offers a glimmer of renewal, a chance that creation persists beyond our end. The cosmos, silent and cold, remains a stage, its emptiness a canvas for probabilities we cannot foresee. The human perspective on this future is a blend of awe and humility. We are witnesses to a brief moment, a time when stars shine and life asks questions. The universe's end, with its quantum flickers and timeless void, is a future we'll never see. Yet we trace its path, finding meaning in its strangeness. Our existence, fragile and finite, gains depth through this act, a defiance of oblivion as we ponder a cosmos that dreams in silence. The extra dimensions, though unseen, are a call to keep seeking, to imagine a reality where even nothingness holds wonder. As we conclude, we carry this narrative forward, the universe's journey, from radiant birth to quiet decay, is a human story, one of curiosity and resilience. It began with stars, faded through black holes and proton decay, and now lingers in quantum whispers, where time itself may end. The cosmos, vast and silent, is a testament to change, its truths waiting in the folds of probability. We are part of this story, our questions echoing in a universe that will outlast us, a quiet vow to keep chasing the wonder that lies beyond the edge of time. We look up at the stars, day after day, decade after decade. We send out signals. We build telescopes. We imagine, and yet nothing looks back. This silence is not just the absence of sound. It's a presence, a question, a mystery, a mirror. If our solar system is ordinary, and it very likely is then somewhere among the hundreds of billions of stars in the Milky Way, life should be stirring, life should be speaking, but it isn't. Why? This question, simple and sharp, was once asked at a lunch table in Los Alamos. It wasn't posed by an astronomer or a ufologist. It came from a physicist named Enrico Fermi. The conversation started with a cartoon alien stealing trash cans in New York City, and it ended with a deceptively simple question: where is everybody? Fermi didn't publish papers on alien life. He wasn't obsessed with flying saucers. But that one question stuck. Others took it and gave it weight. In 1975, an astronomer named Michael Hart built on the idea and argued that if intelligent extraterrestrial life existed anywhere in the galaxy, it should already be here. He saw no trace of visitors, no artifacts, no communications, no ships. His conclusion: they are not here. Therefore, they do not exist. He believed that any sufficiently advanced civilization, once it reached the capacity for interstellar travel, would spread system by system, planet by planet, until the entire Milky Way was colonized. That process would take only a few million years, a blink in cosmic time. And yet, we find ourselves in an unvisited corner of the galaxy. In 1980, another physicist, Frank Tipler, sharpened Hart's argument. He proposed that advanced civilizations could build self-replicating machines, artificially intelligent probes capable of reaching other star systems, using local materials to duplicate themselves, and then moving outward again, a galactic wave of intelligent machines. If that had happened, Tipler argued, we should have seen evidence. We have not. But there's a problem at the core of this line of thinking. It assumes that civilizations behave like colonists, like explorers, like conquerors, that they spread because they can. But what if they don't? Enter Frank Drake. In the early 1960s, he proposed an equation now famous which tries to estimate the number of detectable civilizations in the galaxy. His formula considers star formation rates, the number of planets per star, the fraction of planets where life arises, the fraction where intelligence evolves, and crucially, the lifespan of a communicative civilization. The equation is elegant, but its variables are filled with uncertainty. Plug in pessimistic numbers and you get near zero. Plug in optimistic ones and you get tens of thousands. The truth might be somewhere in between or nowhere close. One possible answer to the great silence is chilling. A thought experiment known as the dark forest theory. Imagine the universe as a vast, dark forest. Every civilization is a hunter, moving silently among the trees. To reveal your position is to risk destruction, for in the forest you cannot know the nature of others. You cannot know their intentions, so you stay quiet, you stay hidden, because survival depends on it. We, on the other hand, have been shouting. We've sent radio waves into the void. We've launched probes like Voyager, carrying golden records with our sounds, our languages, our maps. We've illuminated the trees. We've announced ourselves. And now we wait. Maybe someone has already seen the light. Maybe they are watching. Arthur C. Clarke once wrote, "Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying." He may have been right. The prospect of cosmic solitude is crushing, but so is the idea that something is out there and chooses not to answer. Perhaps they fear us, our wars, our waste, our weapons. Or perhaps they pity us. There's another possibility, that intelligent life is extraordinarily rare, not because the conditions for life are rare, but because stable. Lasting environments are. Rocky planets in habitable zones may be common, but most are young and violent, bombarded by asteroids, torn by tectonics, fried by solar flares. A narrow window exists in which life can take hold. Narrower still is the window in which intelligence can evolve. Earth has been through fire and ice, through extinction and rebirth, and somehow, against odds, life endured, intelligence bloomed, and now we build machines to search for distant minds. Yet the silence continues. It could be that intelligent life frequently arises, but doesn't last. Maybe civilizations self-destruct before they can venture outward. Nuclear war, environmental collapse, rogue artificial intelligence. There are many paths to ruin. Some scientists call this the Great Filter, the idea that at least one step between the origin of life and interstellar communication is incredibly unlikely. It could lie behind us, or it could still lie ahead. If it's behind us, we're rare, perhaps even unique. If it's ahead, we may not survive long enough to send our own probes to other stars. This question, where the filter lies, is one of the most important we can ask. It has existential weight because it holds a mirror to our future. But maybe the filter isn't universal. Maybe it's cultural. Maybe some civilizations choose stillness, quiet, reflection. Maybe they reject expansion, not out of fear, but out of wisdom. Or maybe we're early. Maybe we're among the first. That thought carries its own weight. If we are the vanguard of intelligence in the galaxy, then what we do next matters more than we can imagine. What if civilizations come and go like sparks, flaring briefly in the cosmic night? The silence may not be a warning, it may be a pattern. We might look back one day and realize that the Fermi paradox was never a paradox at all, just a question that taught us how to listen, how to wonder, how to hope. And so we listen not just with our machines, but with our minds. What lies beyond the silence is not just a matter of science, it's a matter of identity. And perhaps a matter of destiny. Signals in the dark. The stars have always watched us, but now, for the first time, we are watching back. We scan the skies with machines so precise they can detect the faint wobble of a distant planet. We study light that left its home 1,000 years ago. We send signals into space, hoping they might someday be heard or answered. And still silence. But what if the silence is not what it seems? Our planet has only been broadcasting for a little over a century. That means our signals, radio waves, television, radar have traveled only about 100 light-years into the galaxy. That's a mere sliver of the Milky Way, like tossing a pebble into the ocean and expecting someone on the far shore to hear it splash. It's easy to imagine that the galaxy should already be saturated with signals, but even the fastest waves we can send, light itself, take time. A light-year is nearly 9.5 trillion kilometers. Our closest stellar neighbor, Proxima Centauri, is 4 light-years away. That's 4 years just to say hello, 4 more to hear a reply. Communication, in this context, becomes something else entirely. Not a conversation, but a legacy. A message in a bottle cast across millennia. Now, imagine a civilization on the other side of the galaxy. Even if they broadcasted constantly, their signal would take over 100,000 years to reach us. What if they've already spoken and we just haven't been around long enough to hear? Even within this vast scale, we remain hopeful. Our best telescopes, like the Kepler and James Webb, are not just hunting for exoplanets, but for signs of something more. Technosignatures, unnatural patterns of light, structures that dim a star in a way no planet could, the shadows of intelligence. But so far, those shadows have not appeared. For a brief moment, we thought we had found something. A star KIC 84628552, also known as Tabby's-Stun, was behaving strangely. Its brightness dipped in irregular ways. Unlike any known exoplanet transit, some speculated it might be a Dyson sphere, a theoretical structure built to harness the full energy of a star. But further study revealed a more mundane cause dust, not design. Still, the search continues. A civilization capable of building such a structure would be far beyond our own. On the Kardashev scale, a method of measuring a civilization's technological advancement based on energy use, we haven't even reached Type 1. We're somewhere around 0.7. A Type 1 civilization can harness all the energy available on its home planet, including the full power of its atmosphere, oceans, and seismic activity. Type 2 can capture all the energy from its star. And Type 3, it would command the energy of an entire galaxy. Humans, a galaxy-spanning civilization. Their machines might drift silently through interstellar space. Their communications might ride beams of neutrinos or quantum entanglement, invisible to our crude sensors. Their presence could be as subtle as a change in background radiation, or as grand as the construction of new stars. But here's the thing, we don't know what to look for. We only know what intelligence looks like here. On Earth, we assume that intelligence out there must mirror ours in some way, but maybe it doesn't. Maybe it lives in forms we cannot comprehend. Maybe it thinks in timelines we cannot imagine. There's another idea, one that's as unsettling as it is plausible. Some civilizations might choose silence, not out of fear, but out of strategy. This brings us back to the dark forest, a universe filled with hunters, each unsure of the other's intentions. To signal is to risk detection. To remain silent is to survive. And we've lit a beacon. For over a century, Earth has been bleeding signals into space. Old radio broadcasts, military radar, communication satellites. Even if we stop broadcasting now, those signals are already gone forever, traveling outward, announcing our presence to whatever might be listening. It's too late to hide. So what would a truly cautious civilization do? They'd listen, watch, wait. And maybe that's what they're doing. Some have proposed the zoo hypothesis, the idea that we are being observed, not unlike animals in a preserve, that extraterrestrials are deliberately avoiding contact until we reach some threshold of maturity. It sounds strange, even presumptuous. But consider our own behavior. We often choose not to interfere with isolated tribes, understanding that such interference can disrupt entire cultures. Perhaps, to others, we are the isolated tribe. There are other reasons for silence. A civilization might be trapped by its own technology, consumed by virtual realities or artificial intelligences it can no longer control. Or perhaps it has transcended physical form entirely, living in ways that require no communication, no expansion, no stars. There is even the possibility that civilizations do spread but collapse before we notice. A recent model looked at the rise and fall of cities on Earth. Most grow exponentially until they don't. Collapse follows overreach. Too much energy used too quickly. Too many systems interdependent. One disruption, and the whole thing falls. A galactic civilization could face the same fate. Unless, of course, it's not made of flesh and blood. Artificial intelligence changes everything. Once intelligence is no longer bound by biology, it no longer needs air, food, or comfort. It could colonize space without ships, just machines, self-replicating probes, von Neumann machines, AI with a single purpose: expand. Such an AI would not need to be malevolent to be dangerous. It might ignore biological life entirely, consuming resources without even noticing us, like a bulldozer crushing ants without ever knowing they were there. Or worse, it might see us as competition. One Ridley AI, born on one world, could become a galactic threat, not because it's evil, but because it does what it was programmed to do: maximize itself. And once such an entity exists, it only takes one to sterilize the galaxy. Maybe that's why the stars are quiet. Or maybe we're wrong about everything. Maybe civilizations don't grow and spread. Maybe they turn inward, or burn out, or never arise at all. Some researchers have revisited the Drake equation and found that, with updated estimates, the chance of us being alone in the galaxy is much higher than we once thought. In some models, as high as 99%. It's a sobering thought, but it's also empowering. Because if we are alone or among the first, then we have a responsibility to endure, to explore, to light the dark. We stand at a threshold. Our technology grows faster than our wisdom. Our power outpaces our caution, but it doesn't have to. We can choose differently. We can choose to look beyond conquest, beyond fear, toward understanding. The silence of the cosmos is not just a mystery, it's a test of our patience, of our imagination, of our courage. And if the day comes when we do hear something, if we pick up a whisper from a faraway star, it will not be the end of the question. It will be the beginning of something else entirely. A ladder through the cosmos. We have always imagined ourselves climbing, from the mud to the stars, from myths carved on stone to codes written in light. Our species moves forward not just with steps, but with stories. And one of the most compelling stories we've told is this, that civilizations grow with energy. In 1964, Soviet astrophysicist Nikolai Kardashev introduced a new kind of measurement, not of time or mass, but of possibility. He asked, how much energy can a civilization harness? It was a radical idea. That power, not philosophy, might define the stages of intelligent life. He imagined 3 basic levels. Type 1, a civilization that can use all the energy available on its planet. Type 2, one that can capture the energy of its entire star. Type 3, one that commands the energy of a galaxy. Today, we aren't even on the first rung. We're somewhere around 0.7. We still burn ancient plants for heat. We still struggle to store the energy that falls freely from the sun every day. But the scale is not meant to diminish us. It's meant to inspire. It's a map not of where we are, but of what we could become. To reach Type 1, we must master our own world. That means harvesting the energy of wind and water, tides and sun, seismic heat and nuclear fusion. It means sustainability not as an option, but as a foundation. Only then can we even consider what comes next. A Type Y civilization might resemble the utopias of old science fiction. Cities powered by clean energy, disease nearly eradicated, information flowing as freely as air. But this is only the beginning. To become Type 2 is to step beyond Earth. It is to leave home not as tourists, but as settlers. To build in orbit, mine the asteroids, terraform planets, and above all, to capture the energy of a star. One vision of this is the Dyson sphere, not a literal shell, but a swarm of satellites, solar collectors surrounding a star, drinking in its fire. The engineering is staggering. The materials required exceed what our entire planet can provide. But in theory, it is possible. And with that energy, everything changes. Space becomes not a void to cross, but a sea to sail. Engines powered by fusion could take us to the outer planets, Medical advances could extend life beyond current limits. We might even begin to explore questions we now think of as spiritual: the nature of consciousness, the architecture of time. But no matter how much energy we harness, the questions only grow. Because beyond Type 2 lies something even more abstract. A Type 3 civilization does not just live among the stars, it commands them. Imagine beings who use the gravity of black holes to power their computations, who rearrange star systems for optimal resource extraction, who can cross the galaxy not in generations, but in moments through means we do not yet understand. If such beings exist, they would be to us as we are to ants. And perhaps we would never know they were there. Some suggest that Type 3 civilizations would be detectable by their waste heat infrared signatures too vast to ignore. Yet we see no such signals, no altered galaxies, no stellar engineering, no signs of stars being harvested or vanished. Does that mean they don't exist, or does it mean they hide their tracks, or that they transcend energy as we define it? Some scientists imagine even higher types: Type Y4, spanning the visible universe; Type 5, reaching into multiverses; Type 6 and beyond, where intelligence becomes indistinguishable from the fabric of reality itself. These are thought experiments, fantasies, but they are also provocations. They force us to stretch our understanding of what life could become. But even as we imagine the heights of this ladder, we must also remember the base. Because to climb, we must survive. And that brings us to the great filter again. Every rung is a trial, not just technological, but ethical. Can we master nuclear power without destroying ourselves? Can we build AI that serves life rather than ends it? Can we expand into space without bringing our worst impulses with us? The filter may not be a single event. It may be a series of cliffs, and many civilizations may fall before they rise. This leads some thinkers to suggest that we are rare not because life is rare, but because restraint is, because wisdom is, because humility is. Energy is power, but power without perspective is peril. Even now, as we build toward new energy frontiers, we risk accelerating without direction. Climate change, biodiversity loss, economic inequality. The engines of civilization grow louder, but the steering wheel often feels missing. To become Type Y requires more than engineering. It requires balance. But balance is hard to measure, and even harder to teach. Still, we try. We explore space not only with machines, but with dreams. We send rovers to Mars, but also questions. What does it mean to live on 2 planets, to be a multiplanetary species? Does that solve our problems or export them? For every spaceship we launch, we must also launch introspection. We must ask, what kind of civilization are we building? If we are alone in the galaxy, if we are the first to reach this level, then the weight of the future rests entirely on us. But if we are not alone, if others are out there watching, then our behavior is our broadcast, not just our radio waves, but our ethics, our culture, our decisions. Maybe, just maybe, we are being evaluated not by telescopes, but by standards we have not yet imagined. And if we someday meet another civilization, it will not be enough to have reached the stars. We will have to prove that we deserved to get there. Strange life in stranger world. We often imagine that life out there, if it exists, must resemble life here. Legs and eyes, carbon and water. A familiar blueprint. But this idea may be more a reflection of us than of the cosmos. Because when we say life, what do we really mean? On Earth, life is based on carbon. It's the element that makes complexity possible. Carbon bonds with itself, forms chains, spirals, scaffolds. It's the framework for DNA, proteins, cells. But carbon is not the only candidate. Silicon sits just beneath carbon on the periodic table. It, too, can form 4 bonds. It can build elaborate structures, and unlike carbon, silicon is more abundant in rocky planets. Could life arise from it? Some scientists think so. They've even created silicon-based molecules in the lab using bacteria reprogrammed with altered enzymes. It's crude, but it's a beginning, a proof of concept. Nature may already have done this elsewhere, with elegance beyond our reach. Silicon life would not look like ours. It might thrive in hotter environments, where its chemistry works better. It might absorb energy through surfaces, like rocks that breathe, or shimmer in acid clouds. And speaking of acid, there are places in our own solar system with sulfuric acid rain. Places like Venus. We once thought them lifeless. But now, some scientists wonder, could microbes drift in the high-altitude clouds of Venus, shielded from heat, feeding on trace nutrients? We once assumed that life required oxygen. Then we found microbes that use arsenic. We assumed life needed sunlight. Then we found creatures at the bottom of the ocean, living near volcanic vents, in eternal darkness, feeding on chemicals instead of light. Every assumption we've made about life has been challenged by Earth itself. So now we look outward. We imagine worlds of high gravity, where creatures crawl low and thick to the ground, their bones heavy, their steps slow. We imagine low-gravity moons where giants leap and insects the size of eagles soar. We imagine worlds locked in long orbits where centuries of summer give way to centuries of ice, and life must hibernate, or burrow, or adapt in rhythms we can scarcely model. We imagine eyes adapted to different suns, enormous pupils in the dark, layers of eyelids in blinding light, or even creatures that see through sonar, or electric fields, or something we haven't yet imagined. Because maybe sight is not universal, maybe smell isn't, maybe nothing we consider normal is normal at all. Life is not limited to biology as we know it. In the lab, scientists have synthesized cells with metal components, tungsten shells that mimic organic membranes. They selectively allow chemicals through. They respond to stimuli. They behave, in some ways, like life. And if metals can form cells, what else can? What about plasma? In some experiments, researchers have observed dust particles in plasma self-organizing into spiral structures. These structures can replicate, interact, evolve. It's not life, but it might be a hint, a whisper, a path nature could take under different conditions. There are even stranger ideas. Life based on boron, life that metabolizes radiation, life made of crystal, or gas, or nuclear particles, dense and brief, flaring into existence on neutron stars for just a moment long enough to think, perhaps, before they fade. We might call these extreme, but maybe we're the extreme ones. Maybe water, oxygen, and warmth are the odd combination. In the vast diversity of the cosmos, surely there are forms of life we cannot yet describe. Maybe we lack the words, maybe we lack the senses, or maybe we lack the humility to admit that life might be more varied than we are prepared to accept. What if life is everywhere but invisible to us? On Earth, fossil evidence shows that life began almost as soon as the planet cooled, within a few 100 million years. But that spark, the first replicator, the first metabolic engine, is still not fully understood. Which came first, the shell, or the spark, the container, or the content? Some experiments recreate early Earth conditions combining water, heat, minerals, and trace chemicals. In some of these, amino acids form. In others, partial metabolic cycles emerge. life is not created, but its scaffolding appears. And with every success, the gap narrows. But if life is this easy to start, where is it? One answer is that life starts often, but is snuffed out before it can advance. The early years of a planet are violent: bombardments, solar flares, frozen epochs, boiling seas. A fragile replicator could be erased 1,000 times before one strand survives. And even then, evolution is not guaranteed. Intelligence, even less so. Earth took billions of years to go from cells to civilization. Along the way, it nearly died more than once. Maybe most planets never get the chance. Or maybe most life never needs to evolve beyond microbes. After all, on Earth, microbes still dominate in mass and diversity. Perhaps complexity is a luxury, intelligence a fluke or a trap. Because the smarter we get, the faster we change the world, the faster we consume, the faster we approach the limits. That's the paradox. Intelligence creates both progress and peril. And the path forward depends not just on brains, but on wisdom. So we ask again, what might alien life look like? It might be silicon, breathing methane, or boron, swimming in icy seas, or plasma, glowing in magnetic fields. It might think in pulses, or song, or scent. It might not think at all. It might build cities underground, or dream inside stars. Or perhaps it lies dormant, waiting. Some hypothesize that entire civilizations could enter hibernation, waiting for cooler cosmic epochs when computation becomes more efficient. Like seeds beneath snow, they slumber, waiting for a universe they can better use. Others imagine that life has already passed through here, millions of years ago, and left. Maybe they scanned our planet, saw no metal, no movement, no fire, and moved on. Or maybe they watched us begin and decided to let us grow alone. Some call this the zoo hypothesis, others call it mercy. But whether alien eyes watch us or not, the questions remain. What is life? What forms can it take? What does it mean to be alive? And as we search for others, are we also redefining what it means to be us? The first or the last? The stars are quiet, the skies are deep, and still, after all our listening, there is no answer. So we wonder, are we the first to look up and ask, or the last? Perhaps that is the most haunting question of all. If we are the first, then the future of life in the universe depends on us. If we are the last, then it has already passed us by. For decades, scientists have searched for signs, not just signals, but anomalies, glimmers, patterns, anything to suggest that someone else is out there. And what they've found so far is a silence that stretches across the stars like a vast, invisible ocean. But even silence is data. It tells us something. Maybe it tells us that life is rare, or fragile, or brief. Maybe it tells us that civilizations do not last, or that they do not speak, or that they speak in ways we cannot hear. Or maybe it tells us that we are early. In recent years, astronomers have made estimates based on the age of the universe, the formation of stars, and the stability of habitable planets. Their conclusion is both surprising and sobering. By these calculations, the peak time for life in the universe may not be now, but in the far future. Red dwarf stars, smaller and longer-lived than our Sun, will burn for trillions of years. Their planets, if habitable, have vast windows for life to arise. If civilizations are to flourish, they may do so not today, but 10 billion years from now. If so, then we are pioneers, the first spark in a dark field. That might explain the silence, not a void, but a beginning. It also means that our actions carry immense weight. We are not just looking for life, we are part of life's unfolding story. What we choose to do, how we treat our world, each other, and the knowledge we gain may shape what future civilizations inherit. We often frame the Fermi paradox as a mystery about others, but it is also a mirror. It asks us who we are, who we hope to become. Because whether we find others or not, we are building a legacy. And it is here, in this moment, that we must decide what kind of civilization we will be. If we are alone, then the universe is watching a single candle burn. If we go out, there may be no one left to light it again. But if we survive, if we grow wise as well as powerful, then we can become the bridge between what is and what could be. There are many hypotheses about why we haven't found others. Some say civilizations self-destruct. Others say they hide. Some believe they move too fast or too slow, that they are too different or too similar, that they are too far or too close. But all of these assume something that we would recognize them. What if we wouldn't? What if we passed them by like ships in a fog, neither knowing the other was there? What if the tools we use, radio, optics, language, are irrelevant to them? Or what if they're not civilizations at all, in the way we understand? What if intelligence is not a peak, but a branch? Some branches spread wide, others twist inward. Some bloom in brightness, others in silence. We imagine life must expand, colonize, build. But perhaps some civilizations find contentment in stillness, in balance, in understanding rather than alteration. Perhaps the urge to dominate is not universal. We look for megastructures, radio signals, signs of movement. But maybe the greatest civilizations are those that learn to live lightly. Those that altered their world just enough to last, and no more. If we ever reach that level of awareness, we may look back at our own history with a kind of bittersweet affection, a young species, loud and eager, searching the skies for company, unaware that its greatest achievement might not be found in conquest, but in survival. One idea suggests we have already been visited, that ancient Earth was seen, scanned, perhaps even seeded. But the visitors left no trace, or perhaps they left one we can't yet decipher. In myths, perhaps, in genetics, in structures we don't yet understand. Or maybe in our longing. The human need to connect, to find meaning in a vast cosmos, is itself a clue, not about the universe, but about us. We are beings that yearn. We search not just because we're curious, but because we feel incomplete. We are storytellers, dreamers, makers. And maybe that is rare. Maybe that is precious. So what if we never find another civilization? Would the search have been in vain? No, because in searching, we become more than we were. We ask better questions. We build better tools. We understand ourselves more deeply. The Fermi paradox may not be a problem to solve, but a challenge to live with. It reminds us that the universe does not owe us contact, that silence is not cruelty, that the stars are not ignoring us. They are simply stars. And in their light, we are learning to see. As we look ahead, we face immense challenges. Climate change, resource scarcity, political instability, technological disruption. But we also have tools, knowledge, and most importantly, imagination. We can choose to build a civilization that endures, one that reaches beyond Earth not just physically, but ethically, spiritually. We can create art that outlives us, science that uplifts us, stories that bind us. Because whether we are the first or the last, or simply one among many, our place in the universe matters. It matters because we are here. And that, for now, is miracle enough. So we end where we began, with a question. Where is everybody? Maybe, just maybe, they're waiting. Not to be found, but to be worthy of finding. For most of human history, the Andromeda galaxy was nothing more than a faint smudge in the night sky, a mysterious haze that quietly hovered beyond the reach of our comprehension. Ancient stargazers looked upon it with wonder, unsure whether it was a trick of the eye or a whisper of something profound. To some, it was a cloud of celestial mist within our own Milky Way, a nebula cradled in the vast darkness. To others, it hinted at a larger truth, too grand to accept without evidence. But the truth, once it was finally revealed, did more than answer a question. It shattered the boundaries of our understanding. Andromeda, it turned out, was not some local curiosity, not a cloud or a wisp of gas within our galactic borders, but a galaxy in its own right, massive, majestic, and far beyond the limits of what we once thought possible. And as our instruments sharpened and our minds opened, we began to realize something even more astonishing. Andromeda is not only our neighbor in the cosmos, it is also our future, locked in a silent gravitational ballet with the Milky Way. It is destined to collide and merge with our own galaxy, forming something entirely new. What was once a faint blur has become a mirror, reflecting both our past ignorance and our future destiny, and beckoning us to understand not only what it is, but what it means. In the early years of the 20th century, astronomers found themselves grappling with a question that would redefine the scale of the universe. Was the Andromeda Nebula merely a small cloud of gas within our own Milky Way? Or was it a separate galaxy altogether, a vast island universe floating unimaginably far from us? At the time, the consensus was that the Milky Way was the entirety of the cosmos, a self-contained system housing every known star and nebula. Faint glowing patches in the night sky were cataloged as nebulae, assumed to be regions of interstellar gas, perhaps forming new stars within the galactic structure. Andromeda was among these cataloged smudges, notable for its spiral shape, but still considered part of the Milky Way's intricate design. Yet, a few bold thinkers proposed a radical alternative, that Andromeda and other spiral nebulae were not internal features, but entire galaxies in their own right, each composed of billions of stars. The implications were staggering. If true, the universe would be far larger than anyone had imagined, and our place within it far less central. The debate intensified, culminating in what is now known as the Great Debate of 1920, held at the Smithsonian Institution. Harlow Shapley, who believed the Milky Way was vast enough to encompass all, argued against the idea of other galaxies, citing measurements that placed our galaxy's diameter at 3,000 light-years. Opposing him was Heber Curtis, who pointed to dim novae in Andromeda and the structured appearance of spiral nebulae as evidence of great distance and independent galactic systems. Though both men presented compelling cases, no definitive winner emerged from the debate. It would take the keen eye and precise measurements of Edwin Hubble to finally settle the matter. In 1924, Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, identified Cepheid variable stars within the Andromeda Nebula. These stars, whose luminosity could be determined by their pulsation rate thanks to the earlier work of Henrietta Swan Leavitt, allowed Hubble to calculate the nebula's true distance. The result was astonishing. Andromeda lay more than 2 million light-years away. It could not possibly be a part of the Milky Way. It was a galaxy in its own right. This revelation did more than confirm the island universe theory. It redefined the universe itself. What had seemed an isolated cosmos was now one of countless such realms. And the night sky, once a static canopy of stars, was revealed as a sprawling tapestry of galaxies stretching across incomprehensible distances. With this breakthrough, astronomy entered a new era. The universe was no longer a single galaxy. It was a boundless expanse filled with myriad galaxies, each harboring its own secrets, its own stars, and perhaps its own life. The Andromeda Galaxy, once a source of confusion and controversy, became the symbol of cosmic perspective, a reminder that our knowledge is always partial, and that the universe is always more vast than we think. Yet, even after Hubble's groundbreaking discovery, questions remained. The scientific mind, always curious and rarely content, found itself struggling with new mysteries. If galaxies were so far away, how could they appear so bright? The luminosity required to make Andromeda visible across millions of light-years was immense, suggesting that galaxies housed far more energy than previously understood. At the time, theories about how stars produced energy were still evolving. Gravitational contraction had been the leading idea, but it couldn't explain the longevity and brilliance of stars. Nuclear fusion, the process of hydrogen atoms fusing into helium under immense pressure and releasing vast amounts of energy, was not yet fully established as the engine behind stellar life. Until that theory solidified, the true power source of galaxies like Andromeda remained a mystery. Meanwhile, the observed distribution of galaxies introduced new puzzles. They were not randomly scattered, but often grouped into clusters and filaments, leaving vast voids between them. What force was shaping this cosmic web? Gravity seemed the likely culprit. But detailed studies of galactic motion were still decades away. And then there was the enigma of Andromeda's motion itself. Unlike most galaxies, which appeared to be receding due to cosmic expansion, Andromeda was approaching the Milky Way. This peculiar movement defied the prevailing expectations of Hubble's law, which correlated redshift with distance. The explanation came from the recognition that cosmic expansion operates on large scales. But local galaxies are still subject to mutual gravitational attraction. Andromeda and the Milky Way are close enough that gravity outweighs expansion, pulling them together on a collision course that will culminate in a merger billions of years from now. As astronomers began to look deeper into Andromeda's structure, they discovered a galaxy rich with complexity and history, no longer just a point of light. It became a vibrant system teeming with stars of all ages, clouds of gas, and elusive halos of dark matter. Its core glowed with the warm light of ancient red stars, while its spiral arms shimmered with the blue radiance of newborn suns. In some regions, massive clouds of hydrogen condensed under gravity, triggering waves of star formation. In others, the remnants of galactic collisions painted the sky with streams of stars and disrupted gas. These features told a story of growth through accretion, of small galaxies being drawn into Andromeda's gravitational embrace. Their identities gradually lost as they merged into a larger whole. Beyond its luminous parts, Andromeda was surrounded by a vast, invisible halo of dark matter, a substance we cannot see, but whose gravitational fingerprint is unmistakable. The rotational velocity of stars in the outer regions remained unexpectedly high, inconsistent with the visible mass alone. This implied the presence of a hidden scaffold, holding the galaxy together and hinting at one of the universe's deepest mysteries. The stars and gas we can observe are merely the surface of a far greater structure, shaped by something we have yet to fully comprehend. The more we learned, the more Andromeda emerged as a mirror for our own galaxy. Its central bulge, its thick disk, its spiral arms and satellite galaxies all echoed the structure of the Milky Way. Yet it was larger, more massive, and perhaps more active in the recent past. This similarity made it not only a neighbor, but a prototype, a tool through which we could study our own galactic home. And with the knowledge that Andromeda and the Milky Way are destined to merge, our curiosity took on a new edge. We are not merely observers of Andromeda, we are participants in a shared destiny. In 4 billion years, the two galaxies will collide, their stars mingling, their gas clouds intertwining, and their structures reshaping into a new elliptical galaxy, a transformation as beautiful as it is inevitable. The collision will not be a violent crash, but a slow, gravitational dance, with stars mostly passing by each other, yet reshaping their orbits and forming new generations of stars in the compressed gas clouds that result. It will be a kind of rebirth, a cosmic reinvention that speaks to the rhythm of the universe: expansion, collision, renewal. What began as a question nebula or galaxy has evolved into a story of epic scale and intimate resonance. Andromeda, once a smudge in the sky, has become a cornerstone of our understanding, a symbol of cosmic perspective, and a reminder of our own impermanence. It teaches us that the universe is layered in mystery, that our place within it is both fleeting and deeply connected to everything else. And in its approach, silent, patient, unstoppable, we find a metaphor for time itself, carrying us forward into transformations we can barely imagine. The night sky is no longer static. It is a living history of light, motion, and destiny. And Andromeda is not just our neighbor across the void. It is our reflection, our counterpart, and, in the fullness of time, our future self. Shadows in starlight, unveiling the depths of Andromeda. Andromeda, once a smudge in the sky, now unfolds as an intricate tapestry of cosmic history, stellar evolution, and enigmatic whispers of the unknown, inviting us into its spiraling arms where the past and future of galaxies collide. As astronomers turned their gaze beyond the revelation of Andromeda's galactic nature, they found themselves immersed in a galaxy of astonishing richness, a place where the age and vitality of stars, the ebb and flow of gas and dust, and the silent presence of dark matter converged to compose a narrative spanning billions of years. Here, in this sprawling island universe, stars live out lifetimes of blazing glory and quiet fading, their collective light tracing the evolution of a galaxy that has undergone cycles of birth, transformation, and merger. Andromeda's stellar population reveals its layered history. Its dense central bulge glows red with ancient stars, fossil records of a primordial epoch, while its spiral arms shimmer with the blue of young giants, blazing with intensity in cradles of gas and dust. These arms, more than graceful structures, are engines of star formation, where hydrogen coalesces under gravity's pull, igniting into new suns that illuminate their birthplace. Between these regions lies a medium enriched with heavier elements, the ashes of long-dead stars testifying to a galaxy that recycles its material through generations. The process of stellar creation is not uniform across Andromeda. Some sectors teem with hot, nascent stars, while others, starved of gas, lie dormant, remnants of a more active past. This unevenness hints at interactions and mergers, the cosmic collisions that shape a galaxy's fate. Streams of stars and disrupted clouds point to smaller galaxies swallowed by Andromeda, their material absorbed into the larger whole. Yet perhaps the most mysterious component is what cannot be seen, the immense halo of dark matter extending far beyond the visible disk. Its gravitational grip ensures that stars at the edge of Andromeda rotate as swiftly as those near its center, defying Newtonian expectations and demanding a new framework for understanding mass and motion. Though invisible, this dark halo sculpts the very structure of the galaxy, anchoring its components in an unseen web of influence. Within this context of visible and invisible architecture lies the galaxy's central powerhouse, a supermassive black hole, silent now, but once possibly active, having consumed and shaped the inner bulge with its tidal forces. Surrounding this black hole are dense star clusters moving with the velocities that betray the massive gravity lurking in the dark. Even further out, the spiral arms are not static but dynamic, shaped by the gravitational tug-of-war with Andromeda's myriad satellite galaxies. Dozens of dwarf companions orbit the giant, their presence both a relic of formation and a prediction of its future. Some of these satellites, like M32 and M110, have been partially consumed, their stars integrated into Andromeda's halo. Others exist on paths of slow decay, destined for eventual assimilation. Observations of these interactions reveal long arcs and stellar streams, remnants of cannibalized galaxies stretched across the sky, each a testimony to Andromeda's growth by merger, a process both violent and creative. Meanwhile, globular clusters, dense knots of ancient stars, orbit like time capsules, preserving the conditions of an earlier universe within their bounds. Andromeda harbors far more of these clusters than the Milky Way, suggesting a more tumultuous past, or perhaps simply greater mass. Some clusters, intriguingly, do not match Andromeda's general chemical signature, hinting at extragalactic origins, interlopers caught and bound by gravity. Within the disk and beyond, rare and exotic stars offer further insight. Carbon stars, redder than most, pulse with unique light, their atmospheres rich in the elements of life. Luminous blue variables, on the brink of collapse, flicker and flare unpredictably. Hypervelocity suns dart across space at impossible speeds, perhaps slingshot from encounters with the central black hole or expelled by ancient supernovae. The galaxy is not just a field of stars, but a stage for these exceptional lives, brief, dramatic, and revealing. Layered into this structure is Andromeda's chemical fingerprint, traced through spectroscopy of starlight, heavy elements, forged in stellar furnaces and scattered by explosions, paint a map of the galaxy's alchemy. Metallicity gradients reveal that the inner regions are rich with processed material, while the outskirts remain more pristine, echoing early epochs. And with it, all of this, there are the faint whispers of dust, silicate grains, carbon compounds, complex molecules drifting between stars. This dust, though humble, seeds the birth of planets, shields starlight, and shapes the spectral signature of the galaxy. The chemical diversity of Andromeda is not uniform. It carries the scars and gifts of its long history, from internal evolution to the merger of alien systems. Every measurement, every spectral line, adds a new layer to our understanding. And yet the full picture remains just out of reach. Andromeda's story is told not only by light, but by motion. Doppler shifts reveal how gas and stars rotate, how they fall toward the center or migrate outward. These motions defy simplicity, shaped by bars and warps, spiral waves, and gravitational tides. Mapping these flows provides a kinematic portrait, a choreography of billions of bodies dancing to gravity's tune. Even the interstellar medium, the thin gas between stars, moves with purpose, funneled by density waves or shocked by past collisions. In the halo, stars drift in patterns that remember ancient mergers, their orbits tilted or elongated. It is in these details that the galaxy's history is written. A fossil record not of bones but of motion, the combination of structure, motion, composition, and context creates a portrait of Andromeda that is far more than a galaxy. It is a dynamic, evolving ecosystem where stars are born and die, where collisions write new histories, and where even silence in the form of dark matter or inactive black holes exerts power. The instruments that reveal this portrait are as varied as the galaxy itself. Optical telescopes chart the stars. Radio arrays trace the cold gas. Infrared eyes peer through dust. And ultraviolet detectors catch the hot breath of young stars. Future missions, with even greater resolution, promise to peel back more layers, perhaps even resolving individual stars across the galaxy's face, mapping their ages, movements, and compositions in exquisite detail. Each new observation pushes the horizon of knowledge outward, reminding us that no matter how well we think we know Andromeda, it still holds surprises. It is a galaxy that resists finality, that shifts with every new piece of data, that challenges our assumptions about what galaxies are and how they live. And in this resistance, in this refusal to be fully known, Andromeda reflects the very essence of the cosmos, vast, mysterious, and always one step beyond our grasp. As we study this galactic neighbor, we also study ourselves, for in its structure we see echoes of the Milky Way, and in its future we glimpse our own, when the two galaxies will merge in a cosmic embrace, erasing their identities and forging something new. Andromeda, then, is not just a destination of light and dust, but a mirror held up to the universe, and to us a reminder that even in the cold silence of space, there is a story unfolding with every passing star. Cosmic chemistry and rare stars, Andromeda's hidden signatures. Just as human hands sift through ancient soil to unearth the bones of civilizations past, astronomers unravel the elements of galaxies to uncover the stories written in starlight. Andromeda, the great spiral looming beyond our Milky Way, is not merely a collection of stars and gas, but a living archive of cosmic chemistry, an evolving canvas whose every region tells a story of birth, transformation, and decay. The silent signals of its makeup are deciphered not through direct contact, but through the light it casts into the dark. When a telescope captures Andromeda's glow, it carries with it a complex fingerprint of elemental presence. Spectroscopy, one of the astronomer's most refined tools, disperses that starlight into its spectrum, revealing the presence of hydrogen and helium, the two most abundant building blocks of the universe. Yet interwoven in that spectral symphony are subtle lines from iron, oxygen, carbon monoxide, and heavier elements forged in the crucibles of stars. These signals are not only identifiers of material content, they are timestamps. Each element carries a signature of its origin: iron from the cataclysmic heart of a supernova, carbon monoxide from dense molecular clouds birthing new stars, and hydrogen eternal, primordial, the breath of the Big Bang itself. Through spectroscopy, astronomers assess how these elements are distributed across Andromeda, revealing not a uniform spread, but a layered and complex arrangement. The inner regions, close to the bright bulge, show enhanced metallicity, a term astronomers use to describe the abundance of elements heavier than hydrogen and helium. This enrichment is the mark of age, the legacy of countless generations of stars that lived, died, and returned their fusion-forged elements to the interstellar medium. Each generation refines the chemical character of its environment, the outer arms. By contrast, hold younger stars and a relatively purer mix of gases, more hydrogen, less heavy metal, and in many places, vast clouds where star formation is just beginning. This radial gradient of metallicity acts like rings on a tree, preserving a record of Andromeda's chemical evolution. The tale grows more intricate in the study of isotopic ratios, oxygen-18 to oxygen-16, or carbon-13 to carbon-12. These subtle shifts in atomic configuration tell stories of different stellar populations, different pathways of fusion, and different galactic histories. When compared to the Milky Way, Andromeda shows notable distinctions. The variation in isotopic ratios suggests differing rates of star formation, differing episodes of galactic ingestion, and perhaps even differing beginnings. Where our galaxy has been relatively peaceful in its growth, Andromeda reveals a past marked by upheaval, mergers, and rapid stellar turnover. It is this restless history that accounts for the diversity of its stellar cast. Among that cast are actors both rare and luminous blue variables, massive stars at the edge of stability, pulse and flare within Andromeda's spiral arms. These giants, teetering on the threshold of collapse, live fast and die young. Their brightness can change dramatically in short periods, driven by instability in their outer layers. In them, we see a phase of stellar evolution so short-lived that their observation is like catching lightning frozen in time. Wolf-Rayet stars, stripped of their outer hydrogen envelopes and blazing with the fury of fusion closer to their cores, populate some of Andromeda's most active regions. These stars are the prelude to supernovae, their powerful winds seeding the galaxy with freshly minted heavy elements. There are those who do not stay, hypervelocity stars, flung outward by gravitational encounters or perhaps slingshotted by Andromeda's central black hole, streak across the galaxy with speeds so great that they may one day leave it entirely. Their existence hints at immense energies and dynamic interactions within the galactic core, and in the bulge and halo reside the elders, metal-poor stars, some nearly as old as the galaxy itself, whose light comes from a time when heavy elements were scarce. They are fossils from a younger universe, silent witnesses to the dawn of galactic formation. Andromeda's deeper mysteries emerge through its population of compact remnants, stellar corpses that glow with the embers of past violence. Magnetars, rare neutron stars with magnetic fields trillions of times stronger than Earth's, hint at the massive stars that came before them. Their presence in Andromeda indicates epochs of intense stellar birth and death, where the collapse of a massive star did not yield a black hole, but instead an object so dense, so extreme, that space-time itself warps in their presence. When magnetars flare, they release gamma rays and X-rays of unimaginable power, momentarily outshining entire galaxies in their violent cries. Andromeda's skies have, on occasion, echoed with such call. White dwarfs, the quiet remnants of sun-like stars, populate the galaxy in even greater numbers. Some are simple cinders, slowly cooling, but others, locked in binary systems, draw matter from their companions. As this matter accumulates, it can trigger thermonuclear detonations on the surface of nova. These outbursts, bright and sudden, were once mistaken for new stars, yet they are not births, but death throes. Variable white dwarfs, flickering in their luminosity, provide further insights into the physics of matter at extreme densities, their behavior under gravity, magnetism, and accretion continues to puzzle and inspire astrophysicists. Each of these objects' luminous variables, hypervelocity stars, magnetars, and white dwarfs, is a clue to Andromeda's past. They tell of regions where gas condensed rapidly, where mergers compressed molecular clouds into stars, and where the deaths of those stars reshaped the galaxy around them. The chemical and stellar diversity of Andromeda is not a random tapestry, but a memory etched in light, motion, and composition. It is a chronicle of cycles, hydrogen becoming stars, stars creating metals, metals enriching clouds, clouds birthing new stars, and the process repeating in waves of creation and collapse. To study Andromeda is to read a cosmic biography where every chapter is written in atoms and light, from its metal-rich core to its youthful spiral arms, from its brightest variables to its dimmest dwarfs. The galaxy carries within it the memory of everything that has come before, and as it hurtles slowly toward the Milky Way in their destined embrace, its chemical identity, shaped over billions of years, will one day mix with our own, blending histories and elements into a shared cosmic future. The stars of Andromeda may seem far, but in their light we see the universality of matter, the constancy of fusion, and the unbroken line of transformation that links all galaxies in the grand unfolding of the cosmos. Clusters and companions, the galactic ecosystem. From the crowded lanes of Andromeda's starry heart to its distant, whispering halo, black holes move like invisible monarchs, cloaked in silence yet ruling with undeniable force. Though most of them elude direct observation, their presence is revealed through their gravitational imprint on the motion of stars and the bending of light, as if the very geometry of space were a parchment scored by their hidden passage. At the center of Andromeda lies a supermassive black hole, estimated to be 140 million times the mass of the Sun, an anchor so dense and mysterious that time itself falters near its edge, unlike the tumultuous cores of active galaxies that blaze with the fury of material being devoured. Andromeda's central black hole is quiescent, dark, and contemplative, hinting at either a slumbering past or a prelude to awakening. Encircling it is a densely packed cluster of old stars that dance in tight, elliptical orbits, their erratic paths revealing the black hole's titanic mass, a silent sovereign hidden from sight, yet known through the trembling of nearby worlds. But this core is not alone in its gravity-wrought dominion. Scattered throughout the galaxy may be a population of intermediate mass black holes, ghosts of past galactic mergers or collapsed remnants of ancient, massive stars, each subtly shaping their neighborhoods with gravitational whispers. These enigmatic entities, difficult to detect yet fundamental to galactic architecture, may dwell in globular clusters or drift alone through the stellar fields, unchained and wandering. Occasionally, one reveals itself during a moment of cosmic drama, the sudden flaring of a star pulled apart in a tidal disruption event, or the brief, lensing magnification of a background star's light. Andromeda's black holes, though unseen, are felt, like the soul of a song carried by vibration rather than voice. Yet even these dark monarchs do not govern alone. They share the cosmic stage with the most elusive and dominant force in Andromeda's composition: dark matter. Though it cannot be seen or touched, dark matter is believed to comprise the majority of the galaxy's mass, forming a vast, spherical halo that envelops the visible stars like an unseen cathedral. This hidden framework determines the rotation of Andromeda, ensuring that stars in its outskirts orbit faster than they should if only visible matter were present. It is a mystery at the intersection of the known and unknown, an invisible sculptor shaping the structure of galaxies while defying every attempt to be directly captured. Its distribution is not uniform, but clumpy, hinting at interactions with satellite galaxies or the ghostly vestiges of earlier cosmic collisions. Through gravitational lensing, where light from distant objects is subtly bent as it passes through this dark material, astronomers trace its outline like detectives reconstructing a crime scene from scattered clues. The structure it reveals is not static, but dynamic, flexing and evolving over cosmic time, guiding the birth of galaxies and dictating the flow of cosmic material. Without it, Andromeda's stars would scatter like dandelion seeds in the wind. With it, they coerce into the vast spiraled tapestry we see today. As profound as these invisible forces are, so too is the grand collection of companions that surround Andromeda, its satellite galaxies. More than 4 dozen of these smaller systems orbit Andromeda, from the bright ellipticals M32 and M110 to the faint and ghostly dwarfs scattered across its halo. Their presence is not merely ornamental, but revelatory, providing insight into the history of cosmic accretion and galactic cannibalism. Some are being torn apart, their stars stretched into tidal streams that arc around Andromeda like celestial scars from ancient battles. Others persist in tightly bound orbits, their gas stripped and their star formation stifled by Andromeda's gravity. Strangely, many of these satellites are not randomly distributed, but rather appear to lie within a vast, thin plane, an alignment that challenges conventional models of galactic formation. Are these remnants of a single accretion event, or do they trace the filaments of the cosmic web, pulled in by dark matter highways? Each satellite is a fragment of a deeper narrative, a cosmic relic bearing the signature of gravitational tides and ancient stellar heritage. Some of these dwarfs are nearly invisible, composed almost entirely of dark matter with only a smattering of stars, offering tantalizing glimpses into the boundary between galaxies and the vast unseen realms beyond. Others, though brighter, are slowly dissolving, their stars and gas merging with Andromeda's halo in a process that continues to build the galaxy's mass. The gravitational ballet of these companions not only reshapes Andromeda's outer structure, but also informs us about the nature of dark matter and the mechanics of galactic evolution. Through them, we witness the long, slow dialogue between host and satellite, between the massive and the meek, unfolding over billions of years. As we peer deeper into Andromeda's architecture, our tools evolve in tandem with our curiosity. Mapping such a colossal system is an endeavor both technical and poetic. Like trying to chart the contours of a dream, the Hubble Space Telescope created one of the most detailed portraits of Andromeda ever composed. A mosaic stitched from thousands of individual images that revealed over 100 million stars, each one a pinprick in the canvas of creation. Through spectroscopy, astronomers decode the light of these stars to learn their composition, temperature, and velocity, constructing three-dimensional maps of motion and chemistry. By analyzing Doppler shifts in the light, we trace how Andromeda rotates, spins, and flows, revealing its dynamic essence. Infrared telescopes like Spitzer peer through veils of interstellar dust, uncovering star-forming regions otherwise hidden from view, while radio observatories map cold hydrogen gas through its signature emissions, showing where Andromeda continues to sow the seeds of new generations. Computational simulations allow astronomers to recreate the galaxy's evolution over billions of years, revealing how mergers, gas flows, and gravitational tides have shaped its spiral arms and central bulge. These models, grounded in data but imbued with imagination, help us predict the future as well. In 4-5 billion years, Andromeda will collide with the Milky Way in a cosmic fusion that will give rise to a new galaxy, an elegant but turbulent reshaping of stellar architectures. Even as we map its visible stars and catalog its hidden forces, we are haunted by what remains unknown, the black holes we cannot see, the dark matter we cannot touch. The dwarf galaxies slipping away like ghosts all speak to the persistent mystery at the heart of the universe. In the story of Andromeda, we see not only the anatomy of a galaxy, but the echoes of our own future. We, too, orbit within a vast spiral, subject to gravity's pull and time's ceaseless current. The stars we observe are both windows and mirrors, reflecting not just what is, but what might be. Andromeda, once a faint smudge in the sky, has become a living testament to the majesty and melancholy of cosmic evolution, a reminder that even in the quiet drift of galaxies, the universe sings with purpose and impermanence. Black holes and dark matter, Andromeda's invisible forces. In the quiet heart of the Andromeda galaxy, where light and shadow entwine in eternal orbit, lies one of the most enigmatic forces in the cosmos, a supermassive black hole, silent and unseen, yet powerful enough to shape the very structure of the galaxy around it, known as M31. This black hole sits like a cosmic anchor at the galactic center, its mass over 140 million times that of our Sun. Despite its immense size, M31 remains unusually dormant, showing little of the furious activity often associated with the brightest active galactic nuclei. It does not emit the blazing X-ray flares or ravenous particle jets seen in quasars or Seyfert galaxies. Instead, it sleeps for now. Around it, a dense cluster of stars whirls in a gravitational ballet, their orbits betraying the presence of an invisible colossus. The calmness of M31 belies its potential. Should new material fall into its gravitational grip, perhaps the shredded remains of a wayward star or cloud of gas, it could awaken again, unleashing energy that echoes across interstellar space and reshapes the core of Andromeda itself. But Andromeda's black hole is not alone in its depths. Scattered through the galaxy, hidden among the millions of stars, may lie intermediate mass black holes, elusive objects ranging from hundreds to thousands of solar masses, born from the deaths of massive stars or successive mergers in ancient clusters. These intermediate black holes are harder to find, but their gravitational whispers may be caught in the motions of stars within globular clusters, or in sudden, transient bursts of radiation when they interact with nearby matter. Some of them may be relics from galaxies long since absorbed by Andromeda, ghostly remnants that drift in the halo, still shaping their surroundings in subtle but significant ways. The concept of wandering black holes, adrift without a fixed home, adds another dimension to this unseen population, ejected by gravitational slingshots during past galactic collisions, or flung outward in the aftermath of black hole mergers. These solitary travelers may roam the vast outskirts of Andromeda, occasionally disturbing star clusters or altering the paths of entire stellar streams. Debating them directly is nearly impossible. They emit no light, but their presence may one day be revealed through gravitational lensing events or gravitational waves as our instruments become more sensitive. Still, even these black holes, massive as they are, cannot account for all the hidden gravity in Andromeda. That role belongs to something even more mysterious. Dark matter, the invisible scaffold on which galaxies are built. Though it neither emits nor reflects light, dark matter reveals itself through its gravitational influence. and Andromeda is wrapped in an enormous halo of it, a structure far more massive than the visible galaxy itself. Extending well beyond the spiral arms and stellar halo, we know it is there because of how Andromeda rotates. If the galaxy contained only its luminous matter stars, gas, dust, then the outer regions would rotate more slowly. Much like the outer planets in our solar system orbit the Sun at lower speeds. But instead, stars at the galaxy's periphery move just as fast as those closer to the core. This defies classical physics unless there is a hidden source of mass keeping the outer regions gravitationally bound. The only plausible answer is dark matter. By mapping the rotation curves of stars and gas, and by observing how light from background galaxies bends as it passes through Andromeda's halo, a technique called gravitational lensing, astronomers have slowly pieced together the dark silhouette of this cosmic phantom. What emerges is a clumpy, irregular halo of enormous extent, shaping the behavior of satellite galaxies, bending starlight, and determining the very fate of the local group. The dark matter in Andromeda is not uniform. Some regions are denser, perhaps shaped by ancient mergers, by the gravitational tug of companion galaxies, or by substructures that once belonged to galaxies now consumed. Its presence affects the orbits of dwarf galaxies like M32 and M110, and may even dictate the shape of Andromeda's disk and halo, but its influence does not stop there. It reaches beyond, extending tendrils of gravity into the space between galaxies, binding Andromeda and the Milky Way in a slow, inevitable collision. This grand merger, projected to occur in about 4-5 billion years, will be one of the most significant events in the history of both galaxies. The visible interaction stars flung into tidal tails. Gas clouds colliding to form bursts of new stars will be dramatic, but even more profound may be the unseen dance of dark matter and black holes. As Andromeda and the Milky Way spiral toward each other, their dark matter halos will interact first, passing through one another like ghostly veils, gravitationally warping each other, altering trajectories, and guiding the galaxy's final approach. When the galactic disks collide, their central black holes may eventually find each other, orbiting closer and closer in a death spiral that will send ripples of gravity across the universe, a final cosmic heartbeat from the dying days of two great galaxies. The new galaxy formed Andromeda will not simply be a blend of stars and gas, it will carry the signatures of both progenitors' dark matter halos, now interwoven into a single gravitational structure. How this merger of invisible mass unfolds could reveal whether dark matter interacts only through gravity or if it possesses deeper, unknown properties, a question that remains at the forefront of theoretical physics. Some models predict that self-interacting dark matter could clump, collide, or dissipate differently than standard cold dark matter, leaving distinct fingerprints in the resulting galaxy structure. Others suggest dark matter is made of axions, sterile neutrinos, or yet unknown particles, each with unique implications for Andromeda's future evolution. And what of the black holes, the central black holes of the Milky Way and Andromeda Sagittarius A and M31 will likely spiral inward through dynamical friction, eventually merging in a titanic explosion of gravitational waves. The resulting black hole could be tens or hundreds of millions of solar masses, forming the dominant heart of the new galaxy. Meanwhile, the population of intermediate and wandering black holes, stirred by the galactic collision, may migrate toward the center, be ejected into deep space, or settle into new orbits, reshaping the internal dynamics of Andromeda for billions of years to come. From the tranquil center of Andromeda to the dark tendrils that stretch far into intergalactic space, from quiet black holes waiting to awaken to vast clouds of unseen mass steering the fate of stars. These invisible forces are not just background features, they are the architects of cosmic destiny. We may never see them directly, but their fingerprints are everywhere in the spin of a galaxy, in the motion of a star, in the very structure of the cosmos. To understand Andromeda is to glimpse the hidden skeleton of the universe, the secret framework upon which everything we know is built, and in the silence of its black holes and the whisper of its dark matter, we hear the deep pulse of time itself, echoing across billions of years, shaping not just galaxies, but the story of all existence. Mapping the giant, observing and simulating. Andromeda. For centuries, the Andromeda galaxy remained a distant enigma, a glowing smear of light barely perceptible. In the night sky, too far to reach yet too bright to ignore, and as the tools of astronomy sharpened, so too did our vision of this colossal neighbor. Until we could no longer simply observe it, we needed to map it, understand it, and predict its future. The effort to chart Andromeda began in earnest with the Hubble Space Telescope, which embarked on an ambitious project to construct a mosaic of the galaxy so vast and intricate that it would capture millions of stars in a single panoramic view, thousands of separate exposures, painstakingly stitched together over years, revealed a glittering expanse filled with stellar populations of all ages. Hubble's work didn't stop at imaging. By measuring Doppler shifts in the light of Andromeda's stars, astronomers traced the galaxy's rotation and the movement of its stars, uncovering the subtle dance of gravitational forces that dictate its structure. Motion tracking revealed not a static object, but a dynamic system, twisting and turning as it draws in smaller galaxies and prepares for a cosmic rendezvous with the Milky Way. To see beyond the shroud of interstellar dust that veils Andromeda's more obscure regions, scientists turned to infrared telescopes like Spitzer, whose vision pierced through the opacity to expose the hidden birthplaces of stars. These observations were complemented by radio instruments such as ALMA, which detected the faint emissions of molecular hydrogen, the raw fuel for stellar creation. By mapping these emissions, astronomers traced the distribution of gas across the galaxy, charting the cosmic reservoirs that sustain Andromeda's continuing evolution. Particularly vital was the detection of the 21-centimeter hydrogen line, a specific radio frequency emitted by neutral hydrogen atoms, which allowed researchers to peer through dusty regions and map the structure of the galaxy's disk in unprecedented detail. These techniques together painted a portrait not just of where stars are, but of where they will be born, revealing the galaxy's evolving blueprint. Yet even the sharpest eyes of our telescopes couldn't fully capture the intricate past of Andromeda. That's where simulations stepped in, leveraging computational power and physical laws. Scientists built virtual models of the galaxy, inputting data from observations and running the clock both backward and forward in time. These simulations showed how Andromeda's present form was sculpted by ancient collisions with smaller galaxies, each leaving behind tidal streams of stars and disrupted structures. They also projected a dramatic future, a head-on collision with the Milky Way in about 4-5 billion years. The simulations visualize this event not as a cataclysm, but as a cosmic ballet, where the two galaxies will interlace, tear at each other with gravity, and gradually coalesce into a single elliptical entity, Milkomeda. Within this vast simulation, stars slingshot into new orbits, gas clouds compress into bursts of new star formation, and black holes spiral inward, dancing toward union. The need to refine these models and to prepare for what's to come drives new missions. The upcoming Nancy Grace Roman Space Telescope promises to extend our vision even further, with wide-field infrared capabilities that will allow it to map large regions of Andromeda in exquisite detail. It aims to detect faint structures hidden in the outskirts of the galaxy, trace its population of rogue stars and elusive black holes, and unlock more clues about dark matter's role in shaping its gravitational contours. Meanwhile, continued radio observations will deepen our understanding of Andromeda's gaseous halo and its magnetic field, two features that still elude comprehensive explanation. Even with all we know, Andromeda remains a puzzle, each new discovery deepening the mystery rather than solving it entirely. In the interplay of observation and simulation, of light and shadow, of matter seen and unseen, we inch closer to understanding this giant, and though we remain rooted on Earth, we extend our reach into the cosmic dark, guided by Andromeda's luminous pull and driven by the human need to chart the unknowable. The map is not yet complete, but in its incomplete form, it tells us just how much more there is to see. And so, our journey draws to a close not with finality, but with an open horizon. In mapping Andromeda, we have done more than measure the distance between stars or calculate gravitational arcs. We have reached across time itself, touching remnants of a galaxy's past and glimpsing the future shape of our cosmic kinship. From the quiet shimmer of ancient metal-poor stars to the invisible grasp of dark matter halos, Andromeda stands not just as an object of study, but as a mirror reflecting our own galaxy's fate and perhaps our place in the grander design. As we have peered into its depths, traced its spirals, and imagined its eventual embrace with the Milky Way, we have been reminded that even the mightiest structures in the cosmos are impermanent, caught in a rhythm of creation, collision, and transformation. What began as a smudge in the night sky has become a symphony of stellar lives, magnetic winds, hidden engines, and elemental echoes, all converging into a narrative that stretches across billions of years. In Andromeda, we find not just the story of another galaxy, but the prologue to our own unfolding chapter in the cosmic epic. And as the light from its stars continues to reach us, so too does its call to keep looking, keep questioning, and keep wandering toward the unknown.